Hello fellow problem solvers. So today we're going to be doing a problem from the 2009 IMO Shortlist, problem number N2. I suggest you try this lovely number theory problem out for a minimum of 20 minutes, ideally an hour to an hour and a half, but not more than 3 hours. If on the other hand you'd like to go along with us, I suggest you give it a go for the next 15 minutes. So now without further ado, let's begin. So the problem says that p of x is x plus a times x plus b, a polynomial, and where a and b are fixed integers. A number n is balanced if it's a product of an even number of primes, not necessarily distinct. So by this definition, 15 is balanced, 3 times 5, which is 75, isn't balanced. So now the problem for A asks, can you prove that you can find A and B such that P1 through P50 are all balanced, and prove that if P of n is balanced for every single n, then A is equal to B. And for this part, you need to find different A and B such that P1 through P50 are all balanced. Now, how do we think about this? Well, this number, if x plus a is, if P of x needs to be balanced, then it's only going to be balanced if both x plus a and x plus b are balanced, or if they're both not balanced. So what I think we need is that both of these are either balanced or unbalanced. Interesting. So, and we're going to have values from a and b need to be both balanced or unbalanced. A plus 1 and b plus 1 both need to be balanced or unbalanced. Actually, no, it starts from a plus 1 and b plus 1. A plus 2 and b plus 2 both need to be the same type of balanced or unbalanced. All the way till a plus 50 and b plus 50 both need to be balanced or imbalanced at the same time. For me, I have sort of an idea where I would go with this now, but I invite you here to pause for 15 minutes and think, not necessarily construct A and B, but think, do A and B have to exist such that both of these are balanced or unbalanced, such that A plus I and B plus I for I 1 through 50 are all both balanced or unbalanced. Like they're the same sort of balance unbalanced thing. And I invite you to take 15 minutes and think about that now. And here's the big idea here. Mind you, in how many ways can you, this is just so beautiful, my God, I can't believe this. And how many ways can you really, like these are either balanced or not. So it's either 1 or 0, 1 or 0. 1 if it's balanced, 0 if it's not. And if you go from 1 to 50, like your first group, there are going to be some combination of 1s and 0s, right? And then when you go to, like if you want another group, if you're going to pick A as 1, if you're going to pick A 0, you're going to use another group where it's also the same combination of 1s and 0s, right? Like the balance and unbalancing, the same combination of 1s and 0s. It can be starting from 1011 till 8000 and whatever, 1061, whatever, I don't care. But here, like the thing that really matters is you don't care about these numbers, you just care that they have the same balanced, unbalanced thing. Now, if you, like, there's a finite number of 1 and 0 combinations they can have, but there's an infinite number of these numbers, of these like fifth-tuples, 50 uples, whatever you call n-tuples. For n equals 50, it's 50 uples. And so that means that there will exist A and B between what I think this is. So every one of these we can think about as representing a number between 0 and 2 to the 50th, I believe, yeah, because it has 50 of these, yeah, 2 to the 50th minus 1, technically. And if you take the first 2 to the 50th tuples, you will have, by the pigeonhole principle, at least 2 which have the same sort of this binary representation, which means for those A and B, you'll have the same balance and balance combination. And ergo, you'll have all of these numbers are balanced. And now this solves part A. Now, what are we going to do about part B? I invite you here with this idea to think like, well, for part B, it really means that you can pick A and B such that for any n, A plus n and B plus n are both either balanced or imbalanced. And now with this, I invite you to take another 20 minutes and try to push the problem further. Here's the next hint. So, assuming the contrary, we would have like a plus n and b plus n are both of the same type and they're different. So let's say like a is less than b. Okay, so we have a plus 1, b plus 1. They're of the same type. And now, all the way till till a plus, what's it going to, a plus b minus a. And b plus something else is going to be the same. And then a plus b minus a plus 1. And if you see, this means that this balancing and balancing thing will have a period starting from some point, right? That's really what is enough and necessary. Starting at some point, it has a period till infinity, which means that the, let's call the balancing function f, that at some point starting from some n plus b is going to be equal to f of n. Starting from for all n greater than some n, there will exist a period p such that this will be true, where f of x is equal to 1 if balanced, 0 if not. So now the question is, can this hold true for some non-zero, mind you this is p fixed greater than 0, that this holds true? Can this be, like, this is what's both necessary and sufficient for the condition to hold true. And here's the thing with problem solving. When you're solving these problems, you have a thing you need to prove, and you ask yourself, what is a different way of looking at that? And also when you find a different way of looking at that, as we have now here, you ask yourself, is this necessary? The question is yes. But is it also sufficient? The question is yes. The answer is yes again. And with that, you know, like, it's enough for you to focus on this, and now this is your problem. Can this happen? You need to prove that it can't. That starting from some n greater than, for all n greater than some big N, there's no period, no fixed period such that this is always true. So now I invite you, if you haven't figured this out, take another 10-15 minutes and try to prove that this can't happen. And the next step for me is, well, let n equal to p times k for some super large k, and then what does that give us? Well, that gives us that f of p times k plus 1. Like, k being super large, it just like we just need p times k to be greater than n. And such a k exists. Like, it's for all k that are greater than n over p, which is a fixed number. And then you have f of this is equal to f of pk. And now, because both of these need to be identical, and mind you, this function is multiplicative, and because like if, actually no, it's not, it's additive, it's not multiplicative. Then, or it's additive modulo 2. Like what? Like we can cancel out the p's. Like if this implies it's starting from some k, f of k plus 1 is equal to f of k. So starting from some number, they are all going to be balanced or imbalanced. And now this is just absurd. Because I said it so seriously, this is just absurd, like it can't hold. But no, it's like at some point, like you'll have k is 2 to the alpha, and then you'll also have k, not 2 to the alpha. You'll have k is equal to a square, and then you'll also have k is equal to prime. Right, so this one has one prime divisor, this one has an even number of them. This is balanced, this is imbalanced, and so like this can't hold true forever. And this solves our problem. It's a quite cool problem. I really hope you tried it out. It's beautiful. It's like quite cute. Like doesn't have any big ideas. And the reason I love it is because like you're not really going, like when you have x plus a times x plus b, like this is your polynomial, and you're not trying to like, oh, manipulate it algebraically and see what happens. Oh, what happens if I look at it this way? Now what's balanced? No, you're looking at it in the way it was given to you. And you're thinking about balanced, imbalanced things because like it's a multiplicative thing. So I just love the problem. And this solves it. And as always, thanks for problem solving.